Chapter 10 ends with section 3 asking the question, is there really a correlation? And to answer that question, we're going to use a hypothesis test for correlation. The first thing we have to do is state our variables. X is the independent variable, that's what we put in L1. Y is the dependent variable from L2. The hypotheses then are stated, as is the level of significance. The null hypothesis is exactly what you'd expect, and that is that there is no linear correlation. That is that rho, the population correlation coefficient, is equal to 0. Now, our alternative hypothesis might say that there is a negative linear correlation between the two sets of data, or that there simply is correlation. In other words, it's not equal to 0, or that correlation is positive. We need to check our assumptions, that is that it's random and normally distributed. That's the same as we've been doing with regression. The test statistic comes from a relatively straightforward equation. It'll also come out of our calculator, as will the p-value. We find our p-value in the calculator as well. The conclusion is exactly what you'd expect. As always, if the p-value is less than alpha, then we reject the null hypothesis. Otherwise, we say that there is not enough evidence to support the alternative hypothesis. The interpretation is when we make the conclusion of what this implies in the context of the problem. Here is the formulas, the actual way that we find a linear regression line. And it starts by finding the average point. When we looked at that computer model, we saw that as well. Wherever you've got information from a sample, you also have information for the population. So you may say to yourself, what is the population linear regression line? And that uses betas. So y equals beta sub 0, that's the y-intercept, plus beta sub 1x, that's the slope. That is the true population linear regression line. We use our model to predict the behavior of that population regression. Okay, so let's look at a question. Is there a positive linear correlation between beer's alcohol content and calories? That will help us set the alternative hypothesis. To determine if there is a positive linear correlation, a random sample was taken of beer's alcohol content and calories for several different beers. Test at the 5% level. So we're going to do a two-variable regression analysis as we did before. That told us that R was 0.9134. And remember, we removed the outlier, so you can see that we removed that outlier. So then we use the formula to find our t-value. The two things that we need are r, which came out of our analysis, and n. Remember that there's one less data point because we threw out the outlier. Okay, so I'm going to pull up a calculator to help us through this. And I'm going to start entering values. So our numerator is R, 0.9134. I'm going to divide that by a radical. I need an open set of parentheses just to force everything inside of that radical. I need another open set of parentheses to tell the calculator I'm talking about the numerator of that radical. I'm going to paste in R. Now it's just R that's being squared, so I don't need parentheses there. I'm going to close parentheses, and it tells me that I have now closed that innermost set of parentheses. I'm going to divide that by, and of course 9 minus 2 is 7, but let's actually use the parentheses on our calculator, 9 minus 2, closing those parentheses. Now there's one more set, it's highlighting that to show us that we've now closed the parentheses that were forming the radical in the denominator, and there is our value for t. We're testing for a positive linear correlation, so the alternative hypothesis is that rho is greater than 0. That means that we're doing a right tail test. Remember, the degree of freedom is n minus 2. N is 9, so the degrees of freedom is 7. We go back to the Gossett student t distribution calculator. We're interested in finding a probability. So we put in that the mean is 0 and the standard deviation is 1. We then enter the degrees of freedom. That is 7 for us. our lower bound because we're interested in rho being greater than 0. So we're finding the area that does not contain our alternative hypothesis. So our lower bound, that is to the left, is our t value. Remember, t was approximately 5.9367. So we enter that. And then we ask for the probability, and it tells us that the p-value is approximately 0.0002889. Remember that the calculator gives us our value as a percentage. So all we did in that next step was convert the percentage into a decimal so that we had our p-value. Of course, that is less than alpha. So we reject the null hypothesis in favor of the alternative. That is, there is sufficient evidence to support the claim that there is a positive correlation between beer's alcohol content and calories. Okay, so now we're going to go through and do this using the information from our calculator. First, we're going to state the variables. X is the alcohol content of a beer. Y is the calorie content of a beer. The null hypothesis is that there is nothing to see. There is no linear correlation. That is, rho is 0. We were asked to test whether rho is positive, that is greater than 0, and our level of significance is 5%. We were told that the sample was random, so that's important, the first part. And then we can make the claim that it's normally distributed if we satisfy two things. So first off, R was 0.9134, and the data looks linear. So both of those things imply that they lie in a line. We also need to check for outliers. Remember that this is after we did that. We found an outlier and we deleted it. From our calculator, we got our t value and our p value. That gives us our conclusion. Remember that the level of significance was 5%, so we're comparing alpha to our p value. And when we do that, we see that the p value is less than alpha. I rounded that to 4 decimal places. So we can reject the null hypothesis. That means that there is sufficient evidence to suggest that there is a positive linear correlation between the alcohol content and the calories for the beers that we studied. In previous chapters, after our hypothesis tests, we've talked about a confidence interval. It'll be a little bit different for linear regression. It would be nice to have a range of values instead of a single value. The range is called a prediction interval. To find this, you need to figure out how much error is in the estimate from the regression equation. This is known as the standard error of the estimate, and it's shown as S sub e. Here's the equation for it, where the sigma, that is the sum of the difference of y and y hat squared, is shown as the sum of squared errors, that is SSE. And when I mean shown, it's actually shown on our analysis as SSE. So that's a nice way to shorten the process of finding the standard error of the estimate, is simply to use the SSE, that is the sum of the squared errors, from our calculator. We then simply have to divide that by n minus 2 and take the square root. So for this example, we find the sum of the squared errors, that is 1,711.825 and change, and divide that by 9 minus 2. So let's see how this looks in a calculator. I'm going to open that. First thing I need to do is take the square root. I need to then open the parentheses so that I can have a quotient inside of that radical. I've copied the sum of the squared errors, so I'm pasting that in. I'm then going to divide that by, and I might as well use parentheses to say 9 minus 2, close those parentheses. It's nice practice to use the grouping symbols, but we need another closed parenthesis to close the radical. We press enter and we get our standard error. So let's look at another example, returning to the anthropologist and the length of the metacarpal bones. So when an anthropologist finds skeletal remains, they need to figure out the height of the person. The height of a person in centimeters and the length of their metacarpal bone in millimeters were collected. Test at the 1% level for a positive correlation between the length of the metacarpal bone and the height of a person. It also asks us to find the standard error. And this is the same data that we saw before. So our x is going to be the length of the metacarpal. Y is going to be the height of the person. Null hypothesis is that rho equals 0. That is that there's no correlation. The alternative hypothesis is that there is a positive correlation. And of course, alpha, we were told, is 1%. We were not told that the sample was random. That could be an issue for us later on. The data does appear to be normally distributed, and we know that because we looked at R. R equals 0.856, that's close to 1, and there are no outliers. So now we need our test statistic and our p-value. So let's look at the data for the bones, and let's look at the statistics. That tells us R, and of course N is 9. So I'm going to copy our R value, 0.856, and go back to the formula for T. So let's pull up a calculator and work through this. So our R value was 0.856. And we're going to divide that by a radical. We're going to open parentheses to keep everything inside the radical, and then more parentheses for the numerator. 1 minus 0.856, that 856 is squared. We're going to close parentheses for the numerator inside of the radical. We're then going to divide by n, which was 9, minus 2, and then of the radical itself, and that gives us t. I'm going to copy that, and I'm going to go to the applications for Chapter 6. I want a Gossett student t-distribution. I want it to be standard, so the mean is 0, the standard deviation is 1. The degrees of freedom is 9 minus 2, or 7. We're interested in finding a probability. We are interested in it being a right tail, and we can paste in our lower bound. That was the t-value that we just found, and that tells us our p-value. So this gives us our test statistic, our t-value, and our p-value. We then state the conclusion. When we've converted that percentage into a decimal, 0.0016 is less than alpha, so we reject the null hypothesis. That is, there is sufficient evidence to suggest that there is a positive linear correlation between the height of a person and the length of their metacarpal. We then want to compute the standard error. So we go back to our analysis. That tells us the SSE. We use that to find the standard error. Let's end this chapter by comparing R squared, that is the coefficient of determination, with S sub E, that is the standard error of the estimate, by asking what would happen if we watered down each of the beers in our sample. If we added an equal amount of water for each quantity of beer, both the calories and the alcohol content would fall by a half as well. There's no alcohol and no calories in water. Remember, again, the outlier has been removed. So let's look at this new data. So here are our watered down beers. So the alcohol content has fallen by a half and the calories have fallen by a half. This then we can compute the R squared, the coefficient of determination. Notice that r squared is the same as before we watered down the beers. For both the original beer and the watered down beer, 83.44% of the variation in calories is explained by the linear relationship between the alcohol content and the calories. That is r squared, the coefficient of determination. This makes sense because both the alcohol content and the calories have both fallen by half. However, the average distance between the linear regression line and the data, as measured by the standard error of the estimate, that is S sub e, has changed. Notice that our SSE is different. When we plug it in for the watered down beers, we get half of the standard error of the estimate for the beers to begin with. The new data is half as far from the linear regression line. For this reason, we say that the standard error, S sub e, is a better measure of how well the linear regression line models the data. Now, the coefficient of determination, r squared, still tells us what proportion of the variation that is explained by the model. And that concludes Chapter 10.